Welcome to the lecture series of linear integrated circuits. In this video, we are going to see about integrator. So, in the previous video, we have discussed about how the op-amp is used as a differentiator. Here, we can go with a simple integrator. So, as in the case of differentiator, so just by replacing the input resistance by capacitance, that op-amp will be used as a differentiator. Similarly, here for an operation of integrator, instead of replacing the input resistance, you can replace the feedback capacitance, feedback resistance with the feedback capacitance. Then this op-amp will be perfectly working as an integrator. So if you provide sine wave, it will provide cosine wave. So this is how this will be working as an integrator. So just connect the feedback resistance. Instead of that, connect the feedback capacitance, connect the input resistance. So, as you know that this negative feedback is given, so the virtual ground concept comes into picture. The potential at this point are termed as 0. So, VA minus VB equal to 0 or VA are equal to VB equal to 0. We can assume that. And the current flowing through the input side will be directly flowing through the feedback side. No current will enter into the op-amp. So when we apply the KCL at this node, the current entering is equal to current leaving. So apply KCL at this node. So you will get the nodal equation as V in minus VA divided by R in. For this current I, we can write V in minus VA divided by I. And for this output side, you can get VA minus V naught. VA minus V naught is the potential between this capacitor. So normally the potential across the capacitor C is equal to, so capacitor voltage is given by C into dV divided by dt, the current flowing through the capacitor. So current flowing through the capacitor is given by I is equal to C into dV by dt. So now I can be written as C into dV by dt. So V in the sense VA minus V naught. So just replacing this VA minus V naught. So CF D into VA minus VF divided by dt. So as virtual ground constant, VA will become 0. So you will get minus CF into dV naught by dt. Hence, both are the current equation. Just replace, just equate these two. You will get V in by R1 equal to minus CF into dV naught divided by dt. So in order to cancel this differentiation, you have to integrate on both sides. So integrate on both sides, you will get with respect to time, you will get 0 to t Vn divided by R1 into dt minus CF integral dV0 divided by dt into dt. So dV naught by divided by dt, you will just directly get V naught. So CF is constant. So you will get V naught equal to integral, so minus 1 by R1 CF integral 0 to t V in dt plus V naught 0. So if you see the output equation, that is V naught output voltage is in terms of input voltage by integration. Okay, so V naught equal to integral V in into dt. So that integration part will be depending upon the value of this R1 and CF. So by properly selecting these values, we can use it as a perfect integrator. So this is the ideal integrator. So now when we go with an ideal integrator, the problem is, so when for low frequency, for low frequency, so see about the reactance, Xc is equal to 1 by 2 pi Fc. Xc is equal to 1 by 2 pi Fc. So the output voltage, if you write in case of input voltage, input reactance, you will get the, for zero frequency, that is f is equal to 0, the xc, that is uh, this will be the x equal to 0, that will be that will be acting as an open circuit. This will be acting as an open circuit. There will not be any voltage present. So it will be acting as an open circuit for low frequency signals. So that is zero frequency signals. In case of your DC, the capacitor will become open circuit. So this will be an open loop op amp. So the gain of open loop op amp is about 10 power 5 to 10 power 6. So for small millivolt, it will reach the saturation. So for lower frequency signals, this circuit will not be working perfectly working as an integrator. So for this reason, we are going with a practical integrator. So we can connect the feedback resistance parallel to the capacitor. So in case of connecting the feedback resistance parallel to this capacitor, what will happen? For low frequency signals, this capacitor will become an open circuit. So that output voltage, that is R, this RF is output voltage or gain is depending upon the value of RF. So now this will be acting as an inverting amplifier in case of your low frequency signals. So the problem of getting high gain and infinite gain value will be avoiding by connecting the feedback resistance at the parallel to the feedback capacitance. So this is how the practical integrator will be working. So this is to avoid the offset voltage and to increase the stability. So if you apply again the portions of KCL at the node A, you will get the equations I1 and I2. So I1 in terms of CF dV naught by dt and I2 equal to minus V naught by RF. According to KCL, you know that I equal to I1 plus I2. So just by connecting those two and replace everything by Laplace transformation, finally you will get this expression for the practical integrator. So by connecting the capacitance and resistance parallel combination in the feedback circuit, the op amp can be working as an integrator. So if you see the frequency response of practical integrator, you will get for certain low frequencies, up to a certain frequency, this will be working as an, that is for low frequency, this will be working as an inverting amplifier. So this is your inverting up to certain frequencies. This will be inverting amplifier. And once the certain frequency reaches, if the frequency increases, the gain starts reducing towards the zero. So this is your 0 decibel frequency, and this is your lower cutoff frequency. Okay, so this is in this portion the circuit will be working as an inverting amplifier, and this portion the circuit will be working as an integrator. So for a perfect integration, the signal frequency, the input signal frequency is greater than the lower cutoff frequency, FL. Okay, so this frequency, so the frequency greater than this frequency, the amplification, that is integration is done. Before that, it is just working as an inverting amplifier for low frequencies. These capacitance will be acting as an open circuit. So the gain will be minus RF by R1. So that is nothing but your inverting amplifier. So once it reaches the lower frequency, the gain gets increased. So the perfect integration is done after this frequency. F is greater than FL. So this is how the practical integrator will be working. Hope you understood. Thank you.